Hello everyone. Now in this video I'll be talking of how you can use a simple LC matching section between a complex load and the source to maximize the power transfer to the load. Okay, so in situations you can have in situations where you have a complex load. Okay, for example, if you're dealing with an antenna, so at one frequency it could be a combination of resistive and inductive load, and at the other frequency it could be capacitive load, so it could be a combination of resistor and capacitor. So if you have a complex load, well, how to match the complex load? This is my load, this is my load with um, the source impedance. Okay, so this RS, actually, well, this RS plus GXX is my source impedance. Okay, so how to do that? Well, the most simple way is to have only two reactive components. Although there are other topologies, you can have more than two reactive components. For example, you can have a pi matching network or a T matching network consisting of more than two matching components, or you can have a cascade of such LC sections if you need lower Q of matchings and so on. Well, the simpler way is to have either you can have this as an inductor or a capacitor, a simple L matching network, okay, in this topology. Um, or you can also have capacitor or inductor. So it depends on your choice what you want. And I mean, the matching section could be a low pass filter or a high pass filter. So for example, in this case, I'm considering the CMUT, which is, well, I've taken this from this source. This is about tunable Q matching networks for capacitive ultrasound transmitters onto the structures of transducers. Mostly, I mean, the load is predominantly capacitive. So at a single frequency where it resonates, you can, at one frequency point, um, you can uh, you can model the equivalent impedance of that transducer by a series RC section. Okay, although the model is not that simple, but yeah, at single frequency you can write the impedance as such. So we are talking of, for example, at resonance. So yeah, um, let's say you measure the impedance, and yeah, the resistance it comes something like this. Okay, so this is, let's say, is the it's not that great. Anyways, this is the resonance frequency. Okay, where if, for example, if you're measuring instead of impedance, if you're measuring the power response of a transducer, then at a frequency at which the maximum power is transmitted to the medium by the transmitter is the resonant frequency, and that's also the operating frequency of CMOS. Now, mostly the CMOS are driven, and the source impedance does not matches with the load impedance for such transmitters, and the load impedance we know is capacitive. So what to do now? Uh, the choice of having, for example, an LC section is that well, one of the advantages of this configuration will be that it's a low pass configuration, you see, and it won't allow any harmonics to pass through. Okay, although you can do the matching with the vice versa, you can have a capacitor L. Yeah, the matching can still be done as such. Yeah, but this is a high pass configuration. So this is a high pass. This is a low pass configuration. Uh, I think I'm making it messy, but you can understand because at low frequencies, inductor is going to be a short circuit and capacitor is going to be open. So yeah, it doesn't. This configuration is not going to pass any harmonics to the CMOS. So yeah, there won't be any harmonic generations. Now let's consider this configuration. So the next step is, okay, if you have this simple two element matching section between the source and the load, well, how to find the reactive components x1 and x2? Okay, so in other words, how to find C1 and C1 and L1. Say L1, let's say L1, C2. So I need to determine how the lump components are evaluated at, let's say, the resonant frequency. Okay, so for an L matching section, the reactive elements x1 and x2, these elements x1 and x2, doesn't matter, they are, it's inductor or capacitor. So yeah, it depends on totally on your choice. You're using high pass, low pass configuration. So the reactive elements, they are determined satisfying the conjugate match criteria. Well, what does this criteria says is that in order to have matching, a perfect matching, uh, the load impedance should match the source impedance. In other words, the real part of the Z input. So this is the input impedance, which is seen looking into the L matching section. So it is you're looking from the matching section. You're looking from the source to the matching section, which is transforming this load, and which is the, or you can say the load which is being transformed by the L section. That is the input impedance seen. That should match the source resistance. And the imaginary part which comes along with because you have a complex load, and that is also going to be transformed. This should be equal but opposite in sign with the XS, which is the reactive part of the source impedance. This could also be inductive or capacitive, but it has to be opposite, so it cancels out. So XS is going to cancel out the imaginary part of Zine, and it all boils down to the situation that, okay, then you have the same source Vs, and you have the source impedance Rs. Now XS has been cancelled with the imaginary part because it's equal and opposite. So you only have the real part of the load. So it's like this now. Okay, that's it. So this is the maximum power transfer will occur when RL is equal to RS, and that's your matching criteria. So that's the conjugate matching criteria, because the imaginary part is equal but opposite in sign, and that's going to cancel with XS, and you're left with RS and RL, and RL is equal to RS. So you can see Vs drops equally across both the resistances, and you have the maximum power transfer. So the power transfer is maximum at this condition. Okay, so that's how you maximize power transfer. Okay, now how to do this job? Well, satisfying the conjugate matching criteria, the reactances can be written as such. Now, if you want to go into the details of how these expressions they come out, have a look at this article in Analog Integrated Circuit and Signal Processing. There is a detailed derivation. I'm not going to talk much about it in this video, but if you want to read more, you can have a look. I'll just post the link of the article in the description down in the video. Okay. So X1, well, it happens in terms of the evaluations of X1 and X2. They happen in terms of the match quality factor. So first thing you need to look at is the quality factor. So if I know what is RT and what is XT, which is the reactance of the capacitance of the transmitter, then I can find what is the Q. And then in terms of those Q, I can find X1 and X2, right? So the first thing you want to do is to look at the quality factor. So where to start? The first thing I'm going to do is, if I have a real transmitter, I'm going to connect this to an impedance analyzer to determine what actual load impedance is. And if I'm interested at the operating frequency, then what is at a single frequency, what this components RT and CT are. So let's go ahead. Now this is a simulated input impedance with available circuit models, and the blue one is the real part of the transmitter. So that's the resistive. Okay, so this is the resistive part. That's actually my RT. So, and this red part is imaginary part in XT. Now my job is to, since I'm interested at maximizing the power transfer at resonance, so I'm going to look at the frequency at which the frequency response is maximum, and that happens to be around 77 kilohertz. So I note down the resonance frequency. That's my operating frequency. F naught, let's say, is 77 kilohertz, and at that frequency I'll look at the resistance. That's in blue, and you can see this, that the peak happens at about, let's say this happens at about 5400 ohms. That's how it looks like. And then I look at the imaginary part at 77 kilohertz, and I see that at the same frequency where it happens is about -2. So you see the scale is minus, which shows the load is capacitive. So yeah, now let's say we are very close to, so yeah, maybe 2.49 into 10 to the power 5 ohms. Now, so I have this. Now I have the impedance. Okay, so I know what is my RT plus JXT is, and you can see from the graph. Well, this is a simulation, but that's actually what happens if you connect your transducer with an impedance analyzer. and then you provide a harmonic signal. So you sweep the frequencies for, let's say, 65 to 90 kilohertz. You find out that the resonance occurs at 77 kilohertz. And then at that frequency, you're interested to know what is the impedance. So, you have seen from, let's say, from the measurement or simulation that RT is about 5400 minus J 2.49 10 to the power 5. So that's my input impedance of CMOS, and that doesn't match with a 50 ohm, let's say, function generator, which I'm going to use to drive CMOS as a transmitter. So yeah, I have a problem. I have to match it. So in order to maximize the power transfer, I can't have a maximum power transfer if there is an impedance mismatch. That's where the matching section comes in. So what is the next step? The next step is to evaluate the components. Okay, what are the components? Well, my configuration is that I'm interested to have a low pass configuration. So X1 is going to be my L1, which is an inductor. And then instead of, inductor here, I have a capacitor to make it a low pass configuration. Okay, so how to find L1 and C2? Now, if you recall, we have this RT and CT. RT, we know this as 5400. And if I go back, I can evaluate this. So this is 1 over omega CT at 2.49 10 to the power 5. And if you evaluate this at at this frequency, which is 2 pi into 77 kilohertz, you find out that CT is about 8.24 picofarads. Okay, so it's a small capacitor. Yeah. Now I have a combination. So what happens is that this is a 5400 ohm resistance in series with 8.2 picofarad capacitor. So this is my CT. Okay, this is my CT. This is not C2. This is CT. Yeah. So now I have this matching section, which is an LC matching section. It's a low pass combination, and actually it's a low pass filter to avoid any harmonics. So I bring the same equations over here. So I know that, well, from the match quality factor, I can evaluate X1 and X2. So all I need to do is to plug in those values, CT and RT over here. So I have CT as 8.2 picofarad, which amounts to the fact that XT is about 2.49 10 to the 5. You see, I don't need even CT value. I need only XT. So XT of 2.49 and 2 to the power 5. And you must remember, this is negative. You see, the scale is negative. This is capacitive loading. The measuring part is totally capacitive at all frequencies. So I need XT. Yeah, so this is minus, and then I need RT, which is the resistive part at resonance, and at resonance this is 5400 ohms. Okay, this is important. So these values are at resonance frequency F0. So once I have, the first thing I'm going to do is to evaluate the quality factor. Just plug in those values and you'll find out that Q comes as 480. That's the match quality factor. Then you can evaluate X1 and X2. Let's assume that to make the matter simple, let's assume that we don't have any reactive part of the source, and that is 0. Okay. So if that is 0, then all you need to do is multiply 480 with the source resistance, and that is how much? 50? Yeah, we are considering 50 throughout, so 50 ohms. So if you do that, you have 24,000. Okay, and what is this equal to? X1 is L1, right? And that is actually omega L1. And if you evaluate L1 will be 24,000 divided by 2 pi into 77 kilos, 77,000, and this comes out to be equal to 0.049 henries. Well, it's a big resistance, but yeah, for theoretical purposes, let's keep it that way. So L1 is 0.049 henries. Okay. Similarly, I can find C2, just plug in the values of RT and XT over here with the quality factor that is equal to 480. You find out that X2 is this, which is equal to 1 over omega C2. And omega is again 2 pi into 77,000 because we are working at resonance. So you find out from this expression that C2 is equal to 77, C2 is 77.4 picofarads. Okay, so I think my job is done over here. So C2 is 77.4 picofarads. Now, how do I verify that if I've done the job correct? So if you recall, what I've said before was that if I have done the matching, the load, the complex load has been perfectly matched to the source load. So the maximum power transfer conditions are are required now, and under those conditions, your source impedance should match with the load impedance. So do I have this? So all I need to do is to look at what Z in looks now. Okay, so if I have these components L and C, or X1 and X2, so if I plug this over here, L and C, which is equal to, C2 is 77.4 picofarads, and X1, for X1, we have an inductor which corresponds to 0.049 henries at 77 kilos. The reactance is this, X1 and X2 is this. Okay, so if you're going to plug these values, let's see the transform impedance of CMUT, Z in. Now Z in, how the source looks at the CMUT is that it looks like that at 77 kilohertz, about 77.6 kilohertz, the transform load, the real part, is 50 ohms. That's what we are looking at. And the imaginary part has gone to 0. Okay. So that's how it is, because we already set XS to 0 ohms, right? That was 0. So now the situation is that with the source or the driver or the generator, the RS has been matched to RL. So, and RL is equal to, again, 50 ohm. That's how the generator is looking into. So that's your Z in, right? So Z in looks like that. I mean, the generator sees the load as matched to its impedance. And these conditions, they satisfy your maximum power transfer conditions or matching conditions. So that's how you do the matching. So if you have to check this, I mean, just wire up these two simple LC matching sections with your complex load. It can be a transmitter, it can be an antenna, whatever it is. So just transform those complex, I mean, do the calculations like this, use the same expressions, and then again take a measurement on an impedance analyzer to see if the matching has been done and you're ready to use your circuit as transmitter to transmit the power and maximize the power. Okay, well, those are just equations, but let me show you another way of doing this very quickly. If I can do that. Yeah, let's discard this. Yeah, if you go over here, there is a website. I mean, it's just like a calculator and impedance matching calculator. So this is WWeb. Yeah, if you go to this website and select the type of matching section you want. For example, we have done this for an L matching section. This is a T matching section. You can have pi matching section. So select any type of matching section you like. So let's verify our calculation with an L matching section. And yeah, we have an LC configuration. So I'll show you. Yeah, so we have this same configuration LC. I mean, you can change the configuration with if you want to pass the DC current or not. So if you're an inductor, you're passing the DC current. If you do not want to pass the DC, then you should have a capacitor over here, right? So let's use the same configuration we have worked with. So this is an online tool. Use it, and it's very quick. So just you don't have to go through all those calculations. Okay, I'm going to put the source resistance at 50 ohms, as I have the source reactance is 0, so let's keep it that way. Then the load resistance is, I remember this was 400, yeah, and your load reactance was capacitive. Yeah, so you see this is R plus JXL. It could be inductive or capacitive. So depending on your situation you have. Yeah, so that's my reactance, the load reactance, and that's my load impedance, which has to be matched to a 50 ohms. These are the results, and you see that inductance is 0.049 henries, and you can just go back and see that, yeah, we evaluated that correctly. The capacitance is about 78 picofarads, which is all right, and that happens for the match Q of 480. You can do this. It also plots the real and imaginary curves for at where the match occurs, and you see the yeah the imaginary part is gone. It's not too high. It should go to 0. Okay. So yeah, you can also do it for other impedance matching network. For example, if you want to add more components, you want to control the quality of match, you can have a pi matching network which has more than 2 components. Okay, and you can just give the frequency of the match, the source resistance, source reactance, load reactance. Give the quality of match. You can change the match quality factor over here as well for pi and t matching networks. And this is going to return you with the values for inductance and source capacitances. In this case, this is CS and CL. So CS is the source capacitance is with the source, and CL is with the load. So if you have to do this analytically, you can do as you can do as such. But if you have to do it in a more convenient way, just go to the WWebs tool and do your calculation for impedance matching. Hope this video helps, and thank you for listening, and have a great day. Goodbye.